right. Thank you so much for the introduction. I actually don't speak French, so hopefully you said nice things about me. So yeah, my name is Daniel Chao. I'm the CEO and co-founder of Halo Neuroscience. I'm actually thrilled to be joined by a couple of users of Halo Sport, our first product, here in Paris. So I don't know if you, Cyril, could you raise your hand? So Cyril's a strength and conditioning coach who works with MMA and CrossFit and powerlifters. And then we have Cassie, CrossFit athlete. So I'd encourage, like after this, when we're all getting a coffee, to seek one of us out to have a further conversation. So, you know, maybe before we get into neurostimulation for athletes, let's just talk about my world, and that is the brain. So I'm a medical doctor by training. I went to Stanford for medical school, and I also got a master's in neuroscience from Stanford. My whole life has been about the brain, and a big part of it was inspired by what was called the decade of the brain. President George H.W. Bush in 1990 announced that the 90s was going to be the decade of the brain, and that was this was in part what inspired me to learn more about the brain and design a career around that. You know, from that, President Obama announced another like multi-$100 million effort. And then also here in Europe, actually 10 times bigger than the US effort. This was announced by the European Commission. So all really exciting, a lot of money flowing into brain research. And I think a lot of people just, they give up on the brain. They think, wow, it's the most complicated organ. It's the final frontier, and therefore it is so complicated we can't do anything about it. So I want to challenge that, and I want to propose that over the course of the last several decades, we have learned a lot, and we have gotten to a point where we know quite a bit, and we can do things today from the things that we learned yesterday. So just very grossly, three aspects of the brain that we should go over. So one, the brain is an electrical organ. Okay, so we've known about this for literally centuries, but over the last several decades, we've gotten much better at analyzing the brain and really understanding how its electrical patterns are manifested in brain function. So here's a picture of someone with, it almost looks like a net of electrodes on the scalp, and you can measure with exquisite sensitivity what is going on inside the brain and its electrical activity. So this is a research tool that allows us to understand the brain's electrical properties, and then, you know, hopefully today we can do things to harness that information to do something with it. Number two is the brain is anatomically organized by function. Okay, so you know, again, this understanding goes back hundreds of years from people injuring a certain part of the brain, and then magically they couldn't see, or they couldn't hear, or they couldn't talk. These so-called lesional studies led to this understanding that the brain is organized by functional anatomy. So we can do much better these days with MRI. So this is an MRI looking at the visual system. And you could see that there's certain parts of the brain that recognize faces, but if you show it a house, that same part of the brain doesn't light up. There's a different part of the brain that lights up. So with these really detailed imaging technologies that we have, we can really study the brain at an anatomic level of exquisite sensitivity. This is another way of analyzing the brain. This is called DTI imaging. So here we could see how the different processing centers of the brain are wired. So by understanding where the processing is happening and how the different processing centers are tethered together, again, we just have a renewed and a more accurate and specific idea as to how the brain is wired and connected, and we can use all of this to our advantage. And the last thing is the brain is so-called plastic. And we all know what plastic is. Plastic is something that we can mold and reshape. think of the brain as a computer circuit that can change on its own. All right, that's pretty magical, right? Like, let's say you have a video card, but you need more memory. You know, these days you would have to go to the store to buy a memory card, but our brain is magical enough so that it could reform itself to do whatever we need it to do. So the word plastic is something that is used, and that I will use is this term called neuroplasticity. So this is the brain's ability to reform itself so that it can be tailored to our purposes. And the way we communicate to our brain, like, this is the way I want you to remodel yourself, is by repeating things. All right, so I want it, like, repetition is such a part of our lives that we just take it for granted, that we repeat things, right? Think about when you're a kid and you're learning languages or math. You just repeated it over and over and over again. Think of yourself as an athlete, as you're training to do different athletic tasks. You just repeat, repeat, repeat. So repeating is a way of telling our brain, like, this is important to me. I want you to remember this. I want you to reprogram yourself so that you can do this better the next time I try it. So this is a really interesting MRI slide of someone who is blind. Okay, this person can't see. This area in the back of the brain is typically reserved for vision. So this person who is blind repurposed the part of the brain typically responsible for vision to literally hear. So they are almost seeing their way through life by listening. It's crazy, right? This is amazing. Like, a visual cortex now turning into auditory cortex. So this is a gross example. There are more subtle things that happen to us every day, but this is illustrative of how significant neuroplasticity can be. Okay. So what are we doing about all of this? And now we're going to slowly move into brain stimulation. So, you know, I would argue that we're not doing enough. So we know a lot about the brain, but all we're doing is throwing drugs at it. So the vast majority of the way that we implement the brain is with a chemical. But the chemical approach, I would argue, is not as is suboptimal. So when you take a drug, it has to go into your gut. From the gut, it goes into your blood, and then it goes all over your body. Okay, so that's a problem. It's needed in the brain, and it goes all over the body. So this is a source of side effects. The small amount of drug that makes it into your brain then also goes all over the place when it's only needed in specific parts of the brain. So here is an example of levodopa, which is the gold standard to treat Parkinson's disease. It only needs to go here, but it goes all over the place and produces more side effects. So this is one of the world's most popular antidepressants, CYMBALTA. Okay, so it works to treat depression, but this is a list of its side effects, right? And with any drug primarily affecting the brain, I could show you the exact same thing. Sure, it works, but you pay a price. Now, what if we could use electricity as a medicine for the brain? Okay, remember, like earlier in my talk, we established that the brain is an electrical organ. It's like this computer circuit. So why not speak its language and use electricity as medicine? Okay, so this is one slide about my last company. It's a company called NeuroPace. So we built basically an implanted computer for the brain. So this, it's not that big. It's the size of a small matchbox. And it is implanted in the skull. 2 electrodes are implanted into the brain. And basically, when the surgeon is done implanting this equipment, this computer has everything it needs to function autonomously for 4 to 5 years. And what it does is that it's constantly listening or monitoring the brain's electrical activity. If it detects an electrical signal suggestive of a seizure about to happen, it proactively delivers a small electrical impulse to the brain to normalize its activity. So this so-called closed loop happens about 1,000 times a day with the patient doing nothing. The only thing they feel is that they have less seizures, and in some cases, 0 seizures. So in a disease model where drugs have largely failed these people, we bring in a device, a medical device that uses electricity as medicine to treat these people. Okay, so here's another example. This is not my last company. This is a gentleman with Parkinson's disease, and you can see the characteristic tremor of the disease. This patient had this neurostimulation implanted, this neurostimulation system implanted. And literally seconds after you turn on the neurostimulator, this is what happens. Okay, you see the symptoms have effectively just melted away, literally seconds after you turn on the neurostimulator. So again, we're using electricity as medicine here. So something that might sound crazy, like maybe not now, but when I started speaking about using electricity as medicine, that might have struck you as crazy to begin with, but it's actually being applied in medicine highly successfully. And in fact, it's a really big business. There's about 5,000 or $5 billion US annual for these companies that sell such devices. But you know, if there was anything, this is the problem. Like, nobody wants this level of surgery. I certainly don't. So you have to be very, very sick to be willing to go through this kind of surgery. So I was inspired to think of ways that maybe, like, what if we could use electricity for the brain in a package that doesn't require surgery? Okay. Like, what if we can use neurostimulation technologies without the surgery? And what we found is, my co-founder and I, what we found is this growing body of literature that started in about 2005, grew to 2,000 papers in the span of 10 years. So there's this technology that wasn't just being used in the lab, but also trialed by credible organizations. So the United States military was training drone pilots and snipers in literally half the time if they paired it with this technology. So it really started to pique my interest to see if this technology had any real meaning behind it. So let's talk about this technology for just one slide. It's called transcranial direct current stimulation, or TDCS. So basically what you do is you put an electrode on your scalp over a particular brain region that you want to treat. You turn on the stimulator for 20 minutes, and what that does is it induces a temporary state of hyperplasticity, or you can think of it as hyper-learning. This temporary state lasts for about an hour. So the brain region that is in hyper-learning, what you do for the next hour is you feed that brain training repetitions. And if you were to do that, you would learn at an accelerated rate. So let's talk about the sports application, because this is a sports innovation conference. So what if we put the electrode over the part of the brain that controls movement in our bodies? It's called the motor cortex. We did that for 20 minutes, and then we did our athletic training. Okay? So think about athletic training and how repetitive it is and how long it takes to learn anything. And also think about the load that you put on the body. I mean, so practice is limited. I think everybody here understands that practice is precious. Like, what can we do to get more out of a given amount of practice? Right? We take protein shakes to fuel the body. What do we do for the brain? We don't do that much. So this is an opportunity to maximize the neurologic gains of athletic training by using neurostimulation. So let's keep going. Halo Neuroscience, we're proud of our research, and this is the way we're a data-forward company. Like, we don't think about markets or products until we have the data to really support that. So we started with a literature review. I've already showed you that slide. Then we started doing our own in-house trials to verify the literature. From there, we started to work with college-level athletes and then Olympic and professional athletes. One of our partners here, Monier, who will be speaking later. So the motor cortex I talked to you about just a second ago, it's this special part of the brain that controls movement, and it happens to sit right above our ears. You can see it in red. So what we did with Halo Sport is we took advantage of a form factor that goes typically right over the motor cortex, and that is headphones. And we built in these special pieces right here, which are effectively the electrodes to target the motor cortex, and I can pass this around. Monier, do you mind? Thank you. Okay, so you'll be seeing this soon enough. This is Halo Sport, our first product, and you know, Halo Sport is just a fancy marketing term for a motor cortex specific neurostimulator. That should mean something to you right now. So just looking over some of the data, again, we're a very data-forward, science-first company. This is looking at elite college athletes. We do 2 weeks of leg training and testing before and after. Half of the athletes train with neurostimulation. The other half of the athletes train without neurostimulation. And these are the results. So the Kaiser Air Squat measures the number of watts produced by the legs. And here we could see 12% improvement in the Halo group versus 4%. And then we tested vertical leap 2 different ways. Again, about 12% in the group that used Halo and about 0 to 1% in the group that didn't. So this was a really nice controlled result that confirmed a lot of our earlier experiments. So now this is working with the United States Olympic ski team. Same kind of experimental setup where we have a control group that does training without Halo Sport and another group that trains with Halo Sport. And here we can track their progress over time. So this goes over about 3 weeks. This looks at the skill and the explosiveness of the jump as measured by a force plate. And you can see that the Halo group gets better by about 31% by the end versus 18%. So this is working with professional baseball players with a company that is closely that's just down the street from us called Sparta. And what Sparta does is they provide force plate software to analyze athletes' movement patterns to see if they're healthy movement patterns. If the movement patterns are not balanced and healthy, then that's a problem. This athlete is actually a setup for injury. So what we can use is we can use the so-called Sparta scan as an assay or a way to measure how the quality of this athlete's movements. For the athletes that have that movements that aren't quite ready for real training because they're at risk of injury, what we can do is we can train these athletes so that their movements are more balanced. And this is a typical scan where Sparta measures across 3 different dimensions, and what you want are for all 3 dimensions to be about equal. So you can see for this athlete, it's quite lumpy. You want all 3 measures around that green line, and this is not the case for this athlete. So this athlete is at risk for an injury. And what you want to do with training is normalize these 3 metrics. And you can plot the normalization over time by using Sparta scan longitudinally. And this is what we see. So the green line, or the green bar is Halo, and we're able to normalize over 4% versus the control group, which is at about 1%. Okay, so this would have been a video. We do work beyond athletics. So the United States military is actually our biggest customer. what we can do is we can accelerate the gains from any movement-based training. So you can think about you know, what soldiers need to do in the military as also movement-based training, and we've been successfully helping some of the country's finest with this. So there's applications in shooting. We work with many endurance athletes. So in the upper right is Andrew Talansky, who is America's top hopeful for the Tour de France. We also think of musicians as athletes. So we're not helping with the creative or emotional side. We're helping with the technical side of what they do. And then, you know, beyond sports, and this gets at, you know, Jay's talk on social innovation. So there's an opportunity for us to use this in a disease model. So to the same extent that we could help, we can help athletes with their athletic training, what if we could help a stroke victim with his or her physical therapy? So we already have a clinical trial ongoing to look at this. And then beyond Halo Sport, you know, there's an opportunity for us to tap into this latent neurologic potential that's in all of us that we don't use, that we can tease out with neurostimulation. So I just would love to have you think about yourself and all the things that you would love to have in your life, but you don't do because it takes too long to learn. So what if you wanted to learn to play guitar? What if you wanted to learn to speak Italian? But you don't even start today because it takes too long. It takes too long to learn. But what if we could use neurostimulation to help you learn faster? Like, what would you think about doing today? So I'll close with that. Again, I'll be here for the rest of the day, and we have I have my two colleagues here who are actual Halo Sport users, so I look forward to speaking with all of you. Thank you.